Now, resistors come in all shapes and sizes, and they're made from a variety of materials to satisfy various design requirements. The picture below shows a variety of resistors. Now, resistors have voltage and current ratings, and subsequently maximum power that they can dissipate. The bands on these resistors tell you the nominal resistance. There are 4, 5, and 6 band resistors. 4-band resistors have the first 3 bands telling you what the resistance is, and the 4th band tells you what the tolerance is. You can click the link to learn how to tell the resistance of a resistor based upon the colored bands. Ohm's law dictates the behavior of a resistor. Ohm's law states that the voltage potential across the resistor is proportional to the current through it, and it's related by the constant of proportionality, resistance, such that V is equal to IR. Now recall our previous example, where we were with an element where we took our V per I. That slope was equal to a constant value, which is now our resistance, R. That is, there is a potential that is needed across an element to drive current through it. The picture below shows that we have a voltage potential V existing across a resistor such that current I is able to flow through it. This is synonymous by saying delta V exists across our element such that I is drawn through our resistor R. Without a voltage potential, no current can flow through our resistor. Thus, Ohm's law is commonly represented as delta V is equal to IR. We are going to drop the delta convention and indicate the potential via plus and minus signs. Now, let's consider the resistor shown below, with a voltage potential VAB that's driving a current IA through a resistor with a resistance R. We can express IA in terms of IB, where IA is equal to minus IB. If we apply Ohm's law consistent with our passive sign convention, our voltage potential VAB across a resistor is equal to IA times R. Or if we express this in terms of an active sign convention, that is, we substitute in minus IB for IA, we can say VAB is equal to minus IB times R, or VBA is equal to IB times R. This is important because our potential is dependent upon the direction of I. A resistor is always going to be a passive device. A resistor can never supply power to our system. Now, a very important assumption is made that our resistor is operating within our linear region. Linearity implies that our voltage is a function of I, and this function is equal to IR. That is, our voltage is a function of current, where R, our resistance, is independent of both voltage and current. This, however, is not true if our resistor is carrying a very high current value, for our resistor will begin to get hot and our resistivity will begin to change. However, we are not going to consider nonlinear resistors. Now, given an element with resistance R, and say we have two currents, I1 and I2, flowing through the element, with corresponding voltages, V1 would be equal to RI1, and V2 would be equal to RI2, that are then opposed across the element to drive our currents I1 and I2. Our total voltage applied would be R times the sum of our currents, I1 plus I2, which is equal to V1 plus V2. This illustrates the linearity of a resistor as well as our superposition principle. Now, the power dissipated by a resistor can be determined via Ohm's law. The potential established across a resistor to drive a current I is expressed as V is equal to IR. Now recall power is our current times our voltage. If we substitute in V expressed by Ohm's law into our power equation, our power would be equal to IR times I, which is equal to I squared R. This term is known as Joule heating, and it's proportional to a current squared running through the element. We can express our power dissipated by the resistor also as V squared per R. Now let us consider an application of Ohm's law as well as Joule heating. Say we have a 12 volt source, i.e. a 12 volt battery, that is applying a 12 volt potential across a 6 ohm resistor. And we want to compute the current through the resistor as well as the power dissipated by the resistor. To begin, we'll apply Ohm's law to determine our current running through a resistor. We know our current running through a resistor is our voltage potential per our resistance. Our voltage potential is 12 volts, and our resistance is 6 ohms. Thus, we are drawing 2 amps through our resistor. To calculate the power dissipated, we can use two formulations. The first is for Joule heat, which is I squared R. Our current is 2 amps, And if we square that and multiply it by a resistance of 6 ohms, we are dissipating 24 watts. Additionally, we can calculate our power dissipated by the formulation of V squared per R. Our voltage to potential across the resistor is 12 volts, and if we square that and divide it by 6 ohms, we would be dissipating 24 watts.